Okay. All right. So you can see basically this is like the most trivial kind of query that exists. You have a select statement that says, okay, we are looking for 3 variables: subject, predicate, object, subject, pred, object. This question mark here means variable. Yeah. And what we do is and this is kind of what you always need to think, what is the kind of query part here? So what is, and that is in the where part of the query. This is a graph matching query. So you can see what we are matching here is simply all the kinds of triples that are in our database. So if I run this, the database will simply return the first 10 triples it comes across, which turn out to be these random triples here, and so on. Now, just as a kind of just as a taster, and then I will move over to Sierra's question. You can replace some of these variables by fixed values. So, for example, here I'm looking for all the subjects that are connected to an object via the RDFS label relationship, and if I do that, then I will get back the term on the left, and then its RDFS label on the right. Okay, so that's kind of like, it's the basic structure. So anything we do in SPARQL is an attempt to match the triple structure of whatever thing we are querying. And in this case here, it is the triple store that Jim provided. And in the question that Sierra asked before, what we try to do is we want to actually match the triples inside of an ontology. Now, the first thing is, like, you shouldn't get confused by the fact that there is OWL, and OWL has zero meaning at this level where we are. There's OWL, whatever you see about OWL is just RDF from this perspective of a SPARQL engine or a query engine. So in this case here, I don't even think that there is, or maybe there's some OWL deprecated in this dump here somewhere. OWL class, yeah. So it in any case, this doesn't really mean anything. So here, this is just a triple. This A is a good thing for you to remember. It's a shortcut triple, so it's a very dirty thing to do, but we do it all the time, which is exactly the same as RDF type. So RDF type is a very typical thing that you will nearly have in all the queries that you will write, which just is used for either checking, okay, are we looking for classes or individuals or properties? Or the second thing is very often, if you have if you have a knowledge graph with lots of individuals in it, you can use this to say, okay, give me all the instances of, let's say, the disease class or something like that. But in any case, this is just a shortcut. And here, this is just a simple triple, saying the subject, RDF type, our class, and then there is this specific operator that you don't know, which is this semicolon that basically is a shortcut for simply. So I could write exactly the same thing here by simply adding this. It should have opened a new window. I have too many things open here in my atom. So by simply do it like this here. For goodness sake. Yeah, 32 gigabytes of RAM. Anyways, so and you see, so here we have the full triple. Here is another full triple. This semicolon just means whatever the next two things are, we attach them to the first subject that we had. So basically, here in this case, omen 100, 200 is an OWL class. It also has RDFS label abductance palsy. It also has dbxref UMLS something and the exact synonym abducans palsy. And to make things a little bit more complicated, and I would recommend to you to never use this structure, but it is also allowed, you can use furthermore the comma to actually do the same thing for the last bit of the triple. So you can see here you have triple one, OMIM, RDFS label, some syndrome, and then the triple two, IAO 142 and PMID, which is attached to this OMIM 50. And then you have the comma, which just says, okay, and now do the triple again, the whole thing, OMIM 50, 142, but now also with the other PMID on board here. So these are the things you will never see. If you work with me or in our world, you will never see this comma. Like this is a very, very extreme shortcut. But yeah, it is just possible. So now let's concretely answer the question that's here ahead. What do I do, like me personally, if I need to figure out how to query an ontology? And what I do is I take the ontology, and the first thing I do is I serialize it into turtle syntax. So the reason why I do that is that if you see this here, this is turtle syntax. This looks roughly like the syntax that you put inside of the where clause in the SPARQL query. Okay, so anything that you find in a turtle file should work also in the where clause of the SPARQL query for you. So so that way, you know, let's say some of the, I will just show you an extreme example now. So let me just see whether I can open a, give me one moment, just so that you maybe. I will just save HPO now as a turtle syntax one moment, so that you can see a bit the extreme pains of what Sierra is asking and what we have to deal with sometimes. So I'm going to Protege here, just hitting save as, and I'm selecting turtle syntax. Okay. I'll just save it in where I am. Where am I? Oh no, this is somewhere where I don't want to be now. Just put it in WS, it's fine. hp.ttl. Maybe not, maybe. Still running. Oh, there you go. Just open it in the text editor because my Atom is becoming too slow with all the stuff I've loaded into it. It's one of the most annoying things of Atom, that if you have like 1,000 projects open, it just gets too slow. Okay, so then you open it as a text editor, and now let me show you the nightmare of SPARQL. So this is, for example, let's look for 000051, and yeah, that's an example. Okay, that's a simple example of the nightmare, but let's say you're interested in, so yeah, you can't see it. I could see whether I can make this somehow bigger. Yeah. No, I had lost it, but I'll find it again. There you go. So here you can see this is how an OWL axiom, an OWL statement looks like when you serialize it into SPARQL, and it is a nightmare of epic proportions. So you see here the phenotype class, which is an OWL class, similar to what we've looked at before, that's connected to an equivalent class statement, which itself has type, some OWL restriction. So this is just one thing that all of these kind of statements have. This is here the has-part relationship in RO. And then another subpart, OWL sum values from, OWL intersection of, boo, 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 me, 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 and then you can see all the way down there. So here, like if, for example, for Mondo, sometimes what we need to do is we need to write SPARQL queries to generate reports of some kind, or we generate QC checks. And if I don't know what to write in order to capture the kind of thing that I want to know, is I'm serializing the ontology I'm looking at into turtle syntax. I look at the turtle and then I copy the whole thing into my UI, and then I start filling in the bits with variables that I need to query for. But in any case, so that is really the worst thing you will ever have to do for SPARQL, when you work with SPARQL. So I just wanted to mention this as a trick to find the correct patterns to look for. Does this answer some of your question?
Thank you. That was really helpful. Yep.
Good. All right. So now let's go back to this here. So the YASQ interface is second home to many of us for various reasons. One is if you don't kill the cache in your browser, these queries actually stay over across sessions. So I recently had to replace my computer, and that's why I lost my 500 nice queries that I have here, but I'm slowly rebuilding them. And once you have like a number of queries in there that is useful for your work, then you can just click through them when you create a new query, copy the ones that already work, and adjust them to whatever you need. So that's kind of like a cool feature of YASQ. But the much more important feature is that YASQ actually comes with like both a web service type thing where you can see here, this is like a URL that encodes the entire SPARQL query to the URL plus a URL shortener. So here I share this with you so you can take a look in your thing. So that is a query. And what we, like Nicole, Sabrina, and me specifically, we use this a lot. So we just write queries, we make a shortcut here in YASQ, and then we share it around with everyone. Then we can help each other fix it, share it back, and we can put it in GitHub tickets to say, okay, look, this is what this query gives me and all this kind of stuff. So this is a really powerful tool to collaborate and help each other out to fix queries. And yeah, so for example, this morning, Kent came in the Mondo chat and asked Nico, how can we get the, or not Nico, he said Mondo team, how can we get the anatomical entities that are associated with our diseases from Mondo? And so I built a query for Kent and I shared it with him through here, and he could immediately open it and see the results. I think I even still have that query here. Don't know, it was a bit slowish, but in any case, so that's kind of like, and here, this is also, here you can have that Sierra just for your own purposes, because it gets rid of some of the, that's a bit more advanced than what I want to go today, but this is for you, so you can see a more complex query that actually looks into parts of a logical definition. So that's just for you to, if you're interested in this kind of stuff.
Thank you. Can I ask a really quick question before you move on? Is that top input box the same as the from clause in SPARQL? Like, do I just put in whatever ontology or RDF graph I want in that top box?
Yeah, you can't, no, so it's, so yeah, I think it's the, so I'm unfortunate, so I have never used from. I'm not sure whether from is to select the subgraphs or to, so whether it's to select the data source, but if it's from distributed SPARQL and it's the data source, then yes, it's similar to that.
Okay, great.
What you need to know though is that here, so for us in our domain, there are like maybe 2 or 3 SPARQL endpoints. So these are endpoints are, so for example, a famous endpoint that you should know about is this Renzi endpoint that we use. So that's the one here, from this here, where here I'll share it with you. So you should, you have it because I shared it with you before in the query. But this is the one that is supported by Jim Balhoff, and it has like lots of these ontologies that we care about in there, plus some other cool feats like some reasoned relationships and all this kind of stuff. So it's this is what we mainly use. But another thing that that you can use, which reflects the why are you trying to be smart now here? There's Chrome, so I just look for this the other way around. OnToBe is the SPARQL endpoint of OnToBe, and so you can see here. This is, I'll share it with you again. This is the other kind of thing that we access quite regularly. This has all of the obo ontologies in it that are, but without changes to them. However, it's also very slow. In any case, this can give us, this helps me sometimes, where, for example, when I was working with Sean and Anita this week on a problem where Anita solved like a kind of QC issue, where we wanted to make sure that no annotation property should ever be used as an object property and the other way around. This check, she developed it in SPARQL, and we wanted to know which ontologies actually fail because of this check. And you can use this kind of, for this kind of endpoints, this is good. It's slow, but it gives you a good idea because it has like subgraphs also. You can see, okay, let's look for this anti-pattern and get the names of all the ontologies back that have that. So this is another good place to look for, if you need to. But yeah, most 80% of the things we usually do is with the Renzi endpoint. So there is no endpoint for the ontologies directly. So you need to have an actual triple store that exposes a SPARQL endpoint so that you can connect YaSQL to it. So you can't just say, oh, please load in this ontology and let me query it. But yeah, that's a little bit of a caveat, I guess. Okay.
Nico, can you just what you said just now? So about the ontology, that there's no specific thing endpoint for the ontology. So how do we know if I want to query Mondo versus when I want to query HPO? Let's say how does it know?
Okay. Yeah, so I have been wrestling with Jim about that topic in Ubergraph. In Ubergraph, you can't. So there's no way to do this. So we always have like little hacks in there. For example, when we look for Mondo classes, we do such a restriction here where we say only look for terms in the Mondo namespace. If you, however, really want to just look inside of Mondo, you do need the OnToBe endpoint, because in OnToBe, every ontology is served up inside of a so-called subgraph, like a named graph. This can be queried using this graph structure. And if you say, for example, graph, and let's say, I'm just going to put this one here. You can put the graph URI here. And then I'll just return S instead. So you can see now here, I use this subgraph query. I'll share it with you in the chat so you can also, oops. This is still terrible with how these interface elements work. Anyway, so I shared this query with you. So here you can see, give me all the class names inside of the eco ontology. So that's a thing that you would need to do here in OnToBe, but it is considerably slower than in the Uber graph endpoint and has some less features. So this is kind of like how you can work around it in any case. So that's here you can do it. In Uber graph, you can't do it. That's the formally correct answer.
Great, thank you.
All right. So far, so I know we haven't done much in SPARQL itself so far, but is there any? This was like the sort of introduction in the infrastructure. I want to mention one more thing infrastructure-wise, but is there any question so far about the ecosystem? Let's say. Anyone that has questions, just interrupt me whenever you feel like it. All right, so now let's talk like for 5 minutes about use cases for SPARQL and non-use cases for SPARQL. These two are very important, both of them. If you go and you work for Chris, you will get, so he has been kind of like subtly trying to divert us from SPARQL towards something that looks more like SQL. For some very good reasons. So for example, so he calls this a semantic SQL. So it's kind of like an SQL type thing that you can use inside of SQLite, if you know what this is. But it is a bit semantically aware. And so the reason why there are multiple ways, so we know that there are multiple ways to interrogate an ontology, of course, but the reason why Chris is pushing towards, at least us as engineers learning semantic SQL is because SPARQL has one huge problem, which is that you cannot optimize it. So SPARQL is just what it is. So if a query takes 150 years, there is nothing you can do about this. Like you can try to change to a different SPARQL engine. Let's say your query is slow in Jena, maybe you're lucky and you can put it in a different triple store in a different engine and it gets faster. But you can't really go and say, let's put an index on this and let's make this, some things that you usually do in an SQL-based setting. And we have many kind of queries. Let me just show you, for example, that's what I want. That's the last thing before we go a bit more into actual SPARQL syntax. We have some queries in ontologies sorry, that's wrong. That we are using regularly. Let me think, where is one? Exact. So this is one that we chewed on last time. Okay, you look at this, and if you are familiar with anything like query languages, you will think that is like nothing. It's the most trivial kind of query. What this is looking for is basically all the exact synonyms in our ontologies, all the terms that all the duplicate exact synonyms in our ontology. So we have different terms have to share the same exact synonym. And you would think, look, that is like the most basic type of thing. This should take a millisecond to run. In fact, this query here takes like 2 hours to run. And if it terminates, yeah, I think it does now. What you need to think is basically that for SPARQL, the biggest problem is that that for like some very conventional queries, which are not very SPARQL-esque, like this, where you really just want to compare fields with each other, SPARQL is not really the best thing. It can be very slow, and I know that there will be many people that on the internet in the wider semantic web sphere that will kill me now. That will say, you can do everything with SPARQL. And I love SPARQL, so I'm saying, yes, we can do many things, but this is an example of a query where SPARQL is just stupid. So you don't want to use SPARQL in a setting like that. This query needs to be answerable in less than a second and not in 2 hours time. What you need to consider is why. So this is like the thing you need to consider when you're building an application. SPARQL should not be the one and only answer for many of your queries. So there are cases for SPARQL and there are not cases for SPARQL. Now let's talk a little bit about the cases for SPARQL. So we have two major use cases across Monarch. No, let's say two major use cases across Monarch for SPARQL. No, let's say three major ones. One is quality control. So this is our this is basically what we do in most of our ontologies. You have like we define a bunch of anti-patterns using SPARQL. So what is an anti-pattern? An anti-pattern is a query that should not exist. Okay, so you the typical workflow is like this. Nicole makes an edit to the ontology. Then Sabrina goes, reviews this pull request, and she says, "Ah, look, why did you use this wrong property here in your pull request?" And then Nicole, yeah, I don't know, this created by slipped into my protege accidentally and I didn't realize it. So, and then they come to me and say, Nico, we have here a case where we accidentally used the wrong property and we need to check to prevent that. And then what I do, or now what Joe and I do, is we build a query like this one where we encode this anti-pattern, which is we query for the mistake, so the wrong thing. We add it to our quality control pipeline, and then each time that we have like that a pull request is made in our ontology, so literally all our ontologies have that, this check is run, and it's checked basically, are there 0 results to this? If so, it's good. If there are more than 0 result, that's bad, and the curators need to go back and fix it. And there are like an endless number of checks that we have implemented, in particular for Mondo. I always keep saying that Mondo is probably the most well-protected ontology on planet Earth. But yeah, so you can look through those in your own time. There, these are not even all of them. There are many other ones that we run on in the other folders here and in some other settings. But in any case, this is like use case number 1. Use case number 2 that we cover is we use SPARQL for generating reports. So for example, let me just take a look here. Now, these are the report queries. So for example, do we have one report here? Yeah, let's look at this one. Okay. Nope, that's empty. So for example, so this is like just like a normal workflow for us. Sabrina and Nicole need to edit a bunch of terms that somehow are connected to each other or are similar to each other, and they need to know something about them. For example, in this case here, they wanted to know all the Mondo terms that are linked to I don't know, something with OMIM and have some abbreviation. Doesn't matter now what it means. So what we do is we use SPARQL to define a query, and then we use Robot, which is our tool for running SPARQL queries in the ontologies in the command line. We use that to just simply generate these tables. So that is, we do this kind of like every week. We have a case like that where we generate tables like that. And we use this feature for thousands of things. So for example, also we use this feature for generating our release notes. So you can see these kind of big tables associated with our releases of the changes that have been made and so on. They're all generated with SPARQL and Robot query. And the last one, which I'm not going to go into now, but just as a sense, so we have been talking only about select, but SPARQL can actually also do update operations. So you can, instead of you running select, SPARQL can also do delete and insert and stuff like that. And this can be super useful to manipulate ontologies in certain ways. So let's say you can match all the ontologies that have certain annotation property. Let's say they have a definition to an OMIM term or something, and with a cross-reference to an OMIM term. We match that, and then we also want to add a different annotation to that term, saying that this term has its definition from OMIM or something like that. Okay, so this is a super easy use case where we use SPARQL also for changing our ontology, so for ontology manipulation. Good. Now let's do a little bit of more SPARQL actual. Okay. So maybe let's start with something slightly simpler.
Can I
so
ask a question?
Yeah, go ahead.
So how about aggregate functions? So let's say I want to know how many cell types are in the cell ontology. So meaning probably leaf nodes.
Perfect.
Unit.
Yep. Great question. Let's do that. Since it's the first question, let's start with that question. So let's ask a slightly simpler question, which is, let me just go and I always copy paste these because I don't want to write all. Let's just for your benefit, let's just write this out. All right. So so what we will do now is very simply, we will count the number of our object properties in our database. So I'm just going to remove this here. So the first thing I do is I'm looking only for object properties. So this is, I'm looking for RDF type. And then that's another cool feature of YaSCUI, by the way. It knows some of the namespaces and it adds them straight away to the prefix section. So I will object property. So just maybe because I didn't say this before, this prefix section is actually very underutilized by us. So we have, usually we define things like OWL, RDF, RDFS, obo, and OWL. But if you look at, for example, the style that Jim Balloff employs, so if you, for example, want to look for something like has part, so, and you have like a query with has part in it, one thing that's really cool is you can just do like this. So you can say, for example, has part, then I think it's 50, but it doesn't matter. So maybe it's 51. So you can do it like this, and then you can make much nicer readable queries. Like you just use, let's say, sub has part part. So that's kind of like one underutilized way. I think it's a very good idea to use these kinds of shortcuts because they make your queries much more readable. Another thing that we started recently is also add a bit more metadata to your query. That's a suggestion by Sabrina to actually say what does this query do. So here we say it counts the number of distinct object properties. Anyways, so let's do this. So first of all, we're doing a distinct, select distinct prop. We match the properties, so let's look at that first. So here is the list, so we can already see from the output here in YaSCUI that there are 964 object properties across this database. But now what we want to do is we also want to, and this is a syntax I can almost never remember here, but let me just look at this because cheating is allowed. Sorry. Might have to guess the syntax, unfortunately. Anyways, I'll just guess it. I know, or I ask Anita, who knows it for sure.
Yes, so it's I write in the comments.
Thank you. Are you sending it in the Zoom comment?
Yes.
Okay. No, that's it. Perfect. So this is count. So this is, oh no, we need to also aggregate it. All right, we need to also group.
Yes.
Prop. So this was stupid query because actually this counts by a number of this is actually a group by for prop. So this would count for each of these properties. We have exactly one occurrence. Now, if we want to know, let's say how many, that's a more smart one. So let me just look at this. How many, maybe this will make this triple store blow up. But I think if we do, can I do count star as count without any parameters like that?
Yes.
Okay, so this gives you a, I mean, you will never need to do this, but this is a first aggregation function. So you can do count, or you can do all the kind of typical arithmetic stuff, like you can do like sums as well, and even other kinds of aggregations. So many things are possible here, but I think count is the most important aggregate that we are using for how many annotation properties or something does your ontology have, and which are the different counts and how often are they used and all this kind of stuff. They're very useful for usage statistics. Anita, did you want to say anything else?
No, I think if you use prop instead of star, is going to be the same result. Yeah.
Okay. Yeah. Good. All right. Yeah. So that is an example of an aggregate query. So this brings us here a little bit into the realms of. So I'm going to go back to this this here. Just going to get rid of that. So this query is a simple query that, look at this is also funny. In YaSQL, actually, if you provide something as a prefix, it even renders it in the results like that. So this is actually the BFO 51 that was matched here, but this is just as an aside. Anyways, so what are the other things that we want to do here? So if you construct your query, the typical phases you go through is you write down your match. So this is kind of like the final thing you want to do. So here, we want to get all the properties plus their labels, and maybe let's just leave it at that for now. Okay, and their labels. And now, so this is usually the first phase. Now the second phase is, what we want is, we also want to ensure that we only look at RO properties. So you can see here, there are many different properties from RO, from GoRel, from Go extensions, from FIPO. And if I see them, I go really mad and I want to just delete them all. But Mondo does the same. So I have to delete Mondo at the same time. What we do here then is we are making a filter. So a filter is basically something that is applied after the fact. So the first thing that is always happening is that the engine is going to match this graph pattern here to your SPARQL dump, and then you can write a filter that does something with it. So a typical filter, for example, that we use is is IRI is a typical one, for example. So we want to only get the properties that are actually IRIs and not the ones that are not IRIs. So that should not change the number, hopefully. In fact, this one thing that you should notice here is it introduced some the fact that I added the label here already introduced some duplication to the results. So you can see one key is although we said distinct up here, you can see basically because it will return distinct results of prop label, what it does is it will go and return all combinations of property label across the entire triple story. So you can see here Whatever this is, it's so ugly, and I really want to know what this is. But anyways, it's a different thing. Like I noticed something and that makes me go crazy. Who put the has start point relationship in the ontology? Anyways, so if one of you finds out where this comes from, that would be appreciated. What it does is it looks at different part of labels, and it sees that actually we have, for the part of relationship, which is BFO 50, it records 3 different labels. One is part of tagged with the English language tag. One is part of without the English language tag, and one is part of with an underscore in it. So it will return all 3 of them. So keep this in mind when you are doing this sort of query. One cool thing you can do, which I use a lot, is I've been doing it in, where was it? Not here, not here, there. So you can do something like this. And this is something I only very recently realized that you can do. So I've never done this previously, but I found it super useful for many tasks that I have. So is there any good example here now? There's no why did it put the anyway? So let's make the restriction first, so that we can see also the good example here. So starts with let me just look at this one here. I think we've changed this recently to let's use this one here. This is actually a very bad example, because recently some people have told me that this is way too slow for bigger ontologies, but I forgot now how this starts with starts. So anyways.
Yeah, first is string, str, which starts with.
That's what it was. Okay, okay, good. Str starts with like that. No. If you can find the command, just send it to me and I will use that. Anyways, so you can see here, the cool thing is, so what we did is we use this filter to say, give me only those properties that are in the BFO namespace, so that start with the BFO thing. So you can see all of these ones have been returned. So they're just 9. And then, so the really cool thing was this part of the query here, which I will share with you in a second. That actually concatenates the results of the other thing. So in this case, the label, so that they all appear in a single row. So rather than having like 50 rows that all have like the BFO 50 in the first and then some different label in the second column, you just put the values for all the columns in this row. This is very useful anyways for report generation. So we are using it now also everywhere when we are generating reports. Okay, so we've done this. That's it. Thank you. So we've done this this filtering. We have done the this group concat as a hack to create nice reports and group things together. And now Anita has shared with me how to correctly do this. So what we so this here, just so that you also understand why this was a problem. So what this is doing here is it's running a regular expression check, turning first the property into a string, which is at the moment an IRI. Don't worry if you don't know what this is. Then it runs this regular expression and checks whether this property matches to it. Anyone who knows regular expression knows that they are computationally extremely costly, and in big triple stores it's usually not advisable to run regular expression checks like that. It's just too slow. So instead it's better to do this, which drops also the execution time a bit. So this is how this looks like. All right, so and therefore this is just a lesson. Just use string starts when you do such things rather than using regex if you can. Okay, so we only have 5 minutes left, but the last important thing that I want to cover today is that, and that is the kind of last language feature that is super important when we build queries, is the not exists clause. So so far we have only looked for actual existing for an existing pattern, which is this here is a triple that exists in the knowledge base. But what we didn't do yet is we may want to exclude certain results because they have a specific feature. So for example, what I want to do is I want to exclude now we are looking for, it's a bit annoying. Let me just switch to class instead, because one moment. Didn't know that an empty not exist clause will cause the entire query to fail. That's also new to me. So yeah, go ahead, Megan, see you later. So you can say something like prop and then RDFS subclass of, let's say, our thing. So I don't know whether, hopefully this will not remove everything, but you can see already this gets quite slow in big triple stores like this. Oops, that got rid of everything, so sorry. Let me just do another one. Which is subclass. All right, so before we had 16 examples, now we have 11. So you can see we here, sorry, I switched to querying for classes because I couldn't find in my head a useful example. So we should rename this here to class if we wanted to have it more readable. But the filter not exist clause, what it does basically is it goes and checks that whatever property we've matched before does not have this information attached with it. So this is very, very useful and you use it all the time. For example, if you want to exclude deprecated classes, so classes that were obsoleted by their editor. So I don't know, like this doesn't make sense now, but something like because there is nothing deprecated in BFO, but in any case, this is something you would see very often across the board in queries that we built. Good. So I think that this was enough for today. Is there any question for about SPARQL? And please let me know if you want any more specific trainings in any more specifically more detailed part of SPARQL. We can arrange that, but I thought like a good overview is probably the useful ones right now. So
what are we planning for next week? Are we going to do RO stuff?
Yeah, so I'm about to, so next time we are going to work with object properties. So this will involve, again, a bit of protege stuff. but we will talk specifically about the semantics of object properties, and we will talk a little bit about RO and its purpose, and you know, what are domains and range constraints, why are they important, yeah, and stuff like that. So I will circulate a new tutorial that I managed to steal from Manchester, which I think is super cool. And hopefully you will have time to go through this. This is very useful because it's more on the individuals level. So it's not on the class level, but it will tell you everything you need to know about transitivity, role chains, functional properties, and everything you need to know about object properties. So hopefully you will do that. I will get it ready tomorrow, hopefully.
And is that our
So
last?
have a great day.
Monica, is that our last lesson? Is that our last lesson for the year? Because then you'll be gone after that.
You can make another lesson. Just offer it and see. I mean,
Okay.
I don't need to be there.
Okay. Yeah. Sounds good. Okay. Thanks.
See you guys later. Bye.
Bye.